Good morning, everyone. Am I audible? Am I audible to everyone? Okay, good morning, everyone. Uh, is the screen visible to everyone? Okay, so let us get started then. Today's topic for discussion is going to be sorting algorithms. We are going to look into three different sorting algorithms, which is bubble sort, selection sort, and insertion sort. But before that, as we discussed yesterday, we are going to be talking about time complexity and how is it that you can calculate the time complexity. Okay, so yes, let us begin. So let me before beginning with the actual time complexity part, let us first understand a few things. So one of those is going to be that all the elementary operations that you perform in your program. So if we consider time complexity, we are going to say that what are the different kinds of operations that are going to take up a certain time in your program. So whenever we consider talking about time complexity, so the first thing that comes to our mind is that when, let us say, I am performing an operation which is a multiplied by b in my program, so is it something that is going to take up time or not? So for this we say that all elementary operations, so let me write it down in this way, that all, so by elementary operations, I mean operations such as multiplication, addition, division, and other such things. So there is this load operation, this as well, uh, load or store operation are going to take unit time. So we call this as unit time. It is based on so whatever least amount of time um, is required for any particular operation, that is referred to as unit time. So we say that all elementary operations like multiplication, addition, loading or storing the data is going to require unit time, right? So some operations which are not elementary are, say for examples, when you perform vector operations. So in C++ you use vectors, and uh, in, let us say, C++, in both these languages you use arrays as well as strings. These operations are not going to take unit time, so we do not call them as elementary operations. Okay, so I suppose this part is clear to you. So let us move ahead and talk about things like, so let me first give you an example and then we are going to move ahead. So say for example that you have two different algorithms. We are now currently, whatever we are talking about is not specific to sorting. We are talking about any algorithm. Okay, so say you have an algorithm where the value, so any algorithm which is, let us say, requiring n as an element. So every time that you say that I am going to have order n square of time complexity for a sort, for let us say a sorting algorithm or any kind of algorithm, if you have the time complexity of order of n square, then n here refers to the number of elements that you are either sorting or the number of times that you are running this loop, right? If it is for an array, if even if you are, let us say, traversing the array twice, you say order of n square, right? So similarly, if let us say it has been given to you that there is this algorithm, first algorithm, which is going to work on n is equal to 100, and it is going to take up time of 50 milliseconds, let us say, and there is this other algorithm, and the same, so the same algorithm, if it works for n is equal to 10 to the power 6, for example, let us say, and you have t, which is the time within which it is going to completely uh, use up this n elements, and it is going to, let us say, take up 4 minutes for. So this is about algorithm 1. If the value of n is, let us say, 100, it is going to take up time 50 milliseconds, and if the value of n is equal to 10 to the power 6, it is going to take up 4 minutes, let us suppose. So this is sort of an example. There is this question that I am going to put up to you next, which you can answer. So let us say you have this other time, there is this other algorithm, algorithm 2, it is going to take up, for n is equal to 100, the value of n is equal to 100, it is going to take up 5 milliseconds, while for n is equal to 10 to the power 6, let us say it is going to take up 10 minutes, right? So the question I am going to put up to you now is, which algorithm do you think is better? Okay, so for those of you who are unable to join the class, can you please try to change your internet service, or either let us say wait for a while and see if you're able to join the class again. Yes, so yes, correct. So a lot of you are answering that algorithm 1 is going to be better. So on what basis did you decide that algorithm 1 is going to be better as compared to algorithm 2? T is equal to 4 minutes is less time. Okay. It is based on the amount of data, correct? Yes. So the actual answer is, obviously it is going to take up t is equal to 4 minutes, which is less time, which is fine. But the main thing with which you compare this time is that for the value of n is equal to 10 to the power 6. So let us say your input is of the value of the range 10 to the power 6. So in that case, this algorithm 1 is going to take up only 4 minutes, while algorithm 2 is going to take up 10 minutes. So we basically compare two different algorithms and what their time complexity. Basically, if we are comparing two different algorithms with respect to their time complexity, we say that any algorithm which is going to take up less time with respect to the input that you have. So we have a very large input. For very large input, if an algorithm is working in less time as compared to another algorithm, then we say that algorithm 1, if it is working in less time, is better, right? So this is something that we wanted to look into. So let us understand another thing here, which is say for example that you have been given some time complexity. So which is, let us say, they say that your algorithm, so you have, let us say, created a program, and that program is going to, let us say, take up n cube time for doing a certain part of your project, and let us say it is going to take up 3 into whatever time, 10 to the power 5 n into n unit of time for performing another operation. So what happens in this case, whenever we consider time complexity, writing down the time complexity, we talk about only the non-constant part. So basically we are going to remove this constant part, and we are going to say that the total complexity of your project or program, whatever you've created, is going to be order of n cube, right? So this is another thing that you should keep in mind. So whenever we write down by adding a certain number here, which is constant in comparison to the other ele element that you have written, so we consider only this part as our total time complexity. Okay. So yes, up till here, has everyone understood everything? Is there any doubt? If yes, then you can post that doubt or your query in the group. Okay. If no, then let us move ahead and talk about a time complexity of a given, let us say, piece of code. So let us please repeat the order of NQ part. So we say that if in case you have a certain time complexity, so let us say that you have created a program, and in that program you are performing an n cube operation, and then you're also performing order of n operation. So let us say for example, you have created, let me give you another example for that. So you are creating a program in which you are doing matrix multiplication, say for example, okay, and you are performing matrix multiplication using order of n cube time solution. So for that, what do? You first use order of n square time to take input, right? In matrix multiplication, if you're going to take input of the matrix, you're going to use two nested loops, and for that you're going to require order of n square time, right? Then you are going to perform matrix multiplication in, let us say, order of n cube time. Okay, so we say that in this case n cube time is for processing the matrix, and then what do? You print the matrix multiplication output that you get, and for that, let us say you are again going to take order of n square time. Okay, so if you say, suppose, right, order of n square plus order of n cube uh, plus order of n square, or if you say n square plus n cube plus n square, this is different and this is different. In this case, if you say this, that it is going to take up this much time, then you can simply write it as order of n cube by removing the rest of the things. Okay, because we say that all of these things are going to work parallelly. Okay, so this is the same thing as we are talking about here, which is order of n cube time. Okay, no, so the time complexity shouldn't be order of n cube plus n. In this case, it is going to be only order of n cube. That is what we are discussing here. Okay, so let us move ahead, and if okay, just give me a moment. um it is going to be, if n is constant, then how, why would, so we're not talking about n as constant here. That is what is time complexity all about. So n is not going to be considered as a constant here. The time complexity that you have given, which is 3 into 10 to the power 6 into n, if suppose you have only this particular part, then if you have only this particular part, then the time complexity is going to be order of n only. We are going to remove the constant part from it. Okay. Okay, so let us move ahead, and now let us take certain examples. So we are going to look into a few examples of, let us say, loops, and also few examples of recursion as well. Okay, so say you have been given this piece of code, and you have to, let us start with the simplest example here. So let us say if you have, for I is equal to 1, I less than equal to n, let us suppose I plus plus, and then you have another loop inside this, which is j is equal to 1, j less than equal to n, j plus plus, and then let us say you are performing certain operation here. Let us suppose sum is equal to I plus j plus sum, for example. So what will be the time complexity for this particular piece of code? The outer loop is going to run n times, and the inner loop is also going to run n times, right? So what will be the time complexity in this case? Oh, sorry. So yes, so I have written down this piece of code where you have this recursive function. So we have the factorial recursive function, which is going to take up as an argument, which is int n as an integer, and then it is going to perform certain operations, and if n is equal to 0, it is going to return 1. Otherwise, it is going to return n into factorial of n minus 1. Right. So can anyone tell me what is going to be the time complexity in this case? Am I audible now? Am I audible to everyone now? Okay, I think yes. Okay, so yes, so it is going to be order of n, not order of n factorial. It is, so why is it so? So how do you move forward? You say that let us suppose I have the value of n is equal to 4, and I am going to move ahead with this call this function with the value of n is equal to 4. So it is going to, let us say, call fact of 4 first, and then once it goes inside and executes this particular part, it says that the next recursive call that I'm going to make is to fact of 3, right? And further, when you go ahead, you say that this is going to be fact of 2, then again fact of 1, and then fact of 0. So once it calls fact of 0, it is going to say that I am going to do this if condition becomes true, and then in this case it is going to return 1 simply. So you say the number of times that you are going to call this particular function is n plus 1 times. So if it is n plus 1, this results to order of n, where you have 1 as a constant, so you remove that, so it becomes order of n, right? So if, say, suppose, now let us consider another example as well. So if, say, suppose along with the recursive function, you are going to also have uh, a piece of code wherein you are going to have a loop, let us say, for example. So if you say that I have, let us say, a function int f, and I am passing a variable I here, let us suppose, and you're going to check if I is equal to 1, then return, let us say, return 1. Otherwise, you have a loop here which is going to be having a loop variable j. It is going to start from j is equal to 1 and go on up till, let us say, j is equal to n, j plus plus, and do certain operations. So let us say it is going to see out the value of j, and otherwise it is going to return j into f of I minus 1. Okay, so you have this function here, and from the main function, so in your program you're also going to have a main function. In the main function, you are going to call this with a certain value. So let us say if you're calling this with value 100, for example. So what is going to be the time complexity for this particular piece of code, where you have this function which is going to be called with the value 100. So the value of I is going to be 100, but this function is recursively going to call itself with the value of I minus 1. So what will be the time complexity here? Yes. So, no, so it is not going to be order of n. It is going to be, let us say, whatever number you write here multiplied by n. Now, why is it going to move this way? So, if you, let us say, do not consider this as a constant, if this takes up a value of m, or let us say even n, so in that case, what is going to happen? You're going to say that every time you call this particular loop, it is going to run, every time you call this particular function, and whenever you are going to make recursive calls, it is going to run a loop of order of n. So it is going to run order of n, that is a loop of order of n, let us say m times, say for example m times or even n times. So you are going to do that, let us say m times. So what will this result to? This will result to order of n into m, right? Because every time it is going to run a loop of starting from j is equal to 1 to j is equal to n, right? So this is what it is going to be. So is this clear to everyone? Shall we move ahead? What is n? So n is this value here up till which this loop is going to run. Okay, let me repeat it once again. So we say that, let us suppose you have been given this function here, and in the main function you are going to call this function with a certain value. So whatever value with which you call it, it is going to run a loop every time, since it is a recursive function. So the number of recursive calls it makes multiplied by the time complexity that this loop is going to take. So if this loop is going to run n times, right? So you have to multiply that with the number of times this loop is going to be executed. What if n is equal to m? If n is equal to n, then the time complexity here will be order of n square. Yes. So in this case, the time complexity is going to be 100 into n. But if we consider, if since we do not know what will be the value of this, wherever I have written this 100 here, it can, let us say, take up a value which is m. If we consider this as m, then it is going to be this. For this particular case, yes, it is going to be 100 into n. Okay. So shall we move ahead, everyone? Let us move ahead and talk about space complexity now. No, so why do you think the loop is taking constant time? Whenever you consider a time, so let us suppose you have only this particular loop. If you have only this part of the loop, how much time is it going to take? It is very simple. If you just do not get into so much details here, if you say that if you have only this particular loop, you are going to say that my time complexity is going to be order of n, right? Why? Because my loop is going to run n times. Now this loop that is going to run n times, you are going to execute this particular loop m times. So m into n will be the time complexity. Okay, let us move ahead. So we now let us also look at space complexity, and one of the important things that we are going to look at is going to be the space complexity of a recursive function as well, and then we are going to understand. Okay, so space complexity is, as one of you had asked me earlier as well, can we consider a variable, if we define, let us say, an extra variable, can we consider that as extra space? So again, no. Like we consider in case of time complexity, we say that something that is constant is not going to be a part of our time complexity whenever we write it. So simply the same thing happens in space complexity as well. So something that is going to be constant, which is, let us say, a space for a variable, is not something that we are going to consider in our space complexity if that variable is, let us say, declared or defined, or is going to take up space n times. Like we say for our array, an array is going to contain n elements, let us suppose, then it is going to take up order of n space, right? So let us move ahead with this and talk about space complexity, and say if I have the same function which I had written earlier, which is for this fact here. So what is the space complexity that this particular uh, function is going to take? Can anyone tell me what will be the space complexity here? Order of 1. Okay, so let us order of n. Okay, order of n. Okay, so let us resolve this thing. Some of you are saying that it is going to be order of 1. Some of you are saying that it is going to be order of n. So let us understand that. So whenever we say that we are going to consider space complexity, so what all things come under space complexity? Let us move ahead and understand that. So whenever you are going to run a recursive function, let us say, for example, you are given a recursive function, and so whenever you have a recursive function, it is going to take up space in the stack. So if you remember, we discussed that for any particular process, you are going to have a stack space, right? And stack is going to store. So do you remember the process image in memory that we discussed in our first class for the bootcamp, where we saw that all the local variables and the pointers are going to be stored on the stack? So we looked at for that in a function which was main. So we, for that particular program, we had only the main function, and the main function was going to take up some space on the stack, wherein it is going to store its local variables and other pointers, right? Just give me a moment, everyone. I'll get back. Yes, sorry for that. Let us continue. So, as I said, first of all, let us go through with that. Do you remember process image in memory, and that we have a part uh, of stack in that wherein we store all the local variables as well as the pointers? Pushkar, you were unable to attend the class. You've tried on different networks. Um, so I don't know what has to be done in that case. Since did you try to switch your device? So let us say try to switch your device once and see if it is working for you or not. Okay, so yes, so you remember process image, right? So for every particular function, for every function that you create, including the main function, it is going to take up some space on the stack. So please focus on this part very. So let us suppose that you have a certain function here. Let me write down a piece of code and then we are going to understand with that. So let us say you have let us say you have the main function, and inside the main function you are calling the factorial function with the value n. Okay, and let us also define the factorial function, which is in fact it is going to take up a variable as an argument, and we check if n is equal to 0, then it returns 1, otherwise it returns n into fact of n minus 1. So please note, we are talking about the space complexity now. We have already seen that it is going to take up order of n time complexity. Let us look at the space complexity that this piece of code is going to take up. So we say every time a function is called, it is going to take up some space on the stack and store its local variables along with the pointers. So similarly, we say that if you are calling this main function, so initially when you start your program with the main function, say for example, so let us consider this is the stack that we have. Okay, so you call the main function. The main function and its local variables are stored in this section of the stack, for example, and it is going to take up, let us say, let us consider this as k bytes. Okay, so what happens whenever you have a program which is running, it is going to take up some space in the stack, and on the stack it is going to store its local variables along with its pointers. So let us suppose that the main function is called and it is going to take up k bytes on the stack. Okay, now the next thing that you do is you call fact of n. You call fact of n, and fact of n with its local variables is going to, let us say, suppose take up some space on the stack. Okay, so let us suppose this is also k bytes. Okay, now the next function, since this is a recursive function, this fact function here is a recursive function. It is going to call fact of n minus 1, right? Next it is going to call fact of n minus 2, and so on, right? So every time this function is going to recursively call itself, it is going to take up k bytes of space on the stack. Okay, and up till which part it is going to take up k bytes of space? Up till fact of 0 comes, and whenever you run fact of 0, it is going to return 1. So as soon as you return 1, this fact of 0 and its space on the stack is going to be removed. Then the rest of, as soon as it returns to the previous function that has called it, it is going to get removed from the stack. But initially you say that it is going to take up certain bytes on the stack. So you say if you include these n calls, so these are basically n plus 1 calls as we saw. If you include these n plus 1 calls plus whatever main function is called, so you have n plus 2 calls function into k bytes, which is your time complexity, space complexity. So this amount of space is going to be considered on the stack whenever you have this recursive call. Okay, so when you remove the constants from here, we consider these k bytes as a constant, and let us say 2 is also a constant. So we say that the space complexity here is going to be order of n. Okay, so is this clear to everyone? Is everyone able to understand this? How is it that we have the space complexity for this piece of code as order of n? Okay, y plus 2 here. So the number of times this function fact is going to be called is n plus 1 times, and plus n plus 1 is for this main function, because we are considering that it is also going to take up k bytes. So we have n plus 2 into k. Okay. So we have, let us say, a constant size of, as Naman has written, that let us say if you have an array of, let us say, constant size. So we are not talking about a particular piece of code in terms of what the value of n could be. So for this particular example which you have given, the value of n is going to be 26. N is obviously going to take up a certain value for any particular program that you're going to run. For another program, it is going to, let us say, if in another program, if you are running, let us say, merge sort, you're doing merge sorting, and you will require some space of n elements. Let us say 26 elements are the number of elements that you want to sort, and let us say using the same algorithm you are going to sort 50 elements the next time. So the value of n is something that is, we are talking about in general terms. Obviously you're going to have something in general, right? So that is what n refers to. Why do we write n here? We could have written some certain number, whatever we call with that function, but we want to tell time complexity generally, right? For So for any, we say for any time that you run this particular algorithm, it is going to take order of n time. Now n is going to be whatever the value of n you want to put in your program. Okay. If instead of a recursive function, if as Akshita has asked this question, which is if instead of this recursive function it was a loop here, then the space complexity will be order of 1 and not order of n. Okay, so yes, this is another interesting part for this. If here, let us suppose you were calculating the factorial by running a loop inside the main function only, and you did not have a recursive function, then in that case the space complexity will be order of 1 only. It will not be order of n, because you are not going to take up this much space on the stack. Then you are not going to have this recursive call of function, which is fact of n to fact of 0 will not be on the stack, and it is going to be taking up this much only order of 1 space complexity. What if it is a lowercase alphabet array? Uh, then what will be the space complexity? Why are you considering different data types? It is only in terms of whatever the value of n is. So if in your program you are considering alphabets, that means if this array is going to be of alphabets, that means you are completely processing all alphabets in your program, right? So again, it is going to be order of n only. It does not really consider the data types into size. Variables are going to take up some space on the stack, right? But these variables are going to come into under these sections only. So if you have a variable inside main, it is going to be under this particular section. That is why we've said that let us suppose this is taking up k bytes. So if you have certain variables, let us say it is going to take up k bytes. K in your case can be, let us say, space for one variable or even two variables. How is the time complexity of algorithms in terms of log? Like for binary search, the time complexity is order of log n. So in case of binary search, you should have asked this question at that particular time when we were talking about binary search. But anyway, if you consider binary search, so we are talking now in specifically in terms of binary search, it is going to be running for log base to n times. So for any, so take up an example, you should do this yourself. So go ahead after the class, take up an example of any array for binary search which has n elements. So if you have n elements in your array, you are going to see that the loop or even the, if you are making it a recursive one, it is going to execute log base to n times. So calculate log base to n with calculator and see that your loop is going to run these many times only, and in this much time it is going to find out the element that you're searching for using binary search. Okay. What will be the space complexity of above three examples? So in this particular case, we say that here again, since you have a main function and in the main function you are calling this function f. So similarly, you see here you are running a loop, but loop has nothing to do with the space complexity. So but you are calling these functions, and these functions are going to take up space on the stack. So here also it is going to be order of n space for this particular example. For fact also, this is the same example that we have just looked at, order of n space complexity. This is going to take up order of 1 space complexity, which is, it is not going to take any extra space since you're just running a loop. Okay. Okay, so let us now move ahead. We have spent quite a lot of time talking about time and space complexity. The topics that we had to look into today were sorting algorithms, which is bubble sort, selection sort, and insertion sort. So let us move ahead with that. But before, let us look into some certain things and some certain criteria which you are going to consider when you are going to talk about sorting algorithms in general. So what are the different criteria that you are going to consider whenever you are going to compare two different sorting algorithms? Okay, let us look at that as well. Yes. So let me write this down as the criteria for comparing So this is the criteria for comparing sorting algorithms. Let us look at what are the different things that you need to look at whenever you are considering a particular sorting algorithm. So the first thing here is going to be if so as you have already seen the time complexity, how much time is a particular sorting algorithm is going to take up. So you know what time complexity is. The second criteria is going to be the space complexity. If your sorting algorithm is going to take up some extra space, then it is going to be having some space complexity. Otherwise, it is going to be order of 1. Now, let us look at and understand another term which is in place. So, does anyone know what is in place? What do you mean by a sorting algorithm to be in place? Okay, Anshika and Priyanshu, please keep your questions for toward. We are going to discuss these towards the end of the class because we have less time for discussing the actual topics that we had to discuss today. Yes, correct. So as a lot of you are giving answers to what in place is. So in place means that any particular algorithm which does not require any extra space is going to be called as an in place algorithm, right? So similarly, if your sorting algorithm does not require any extra space, which means that the space complexity is order of 1, that means this particular sorting algorithm is going to be an in place sorting algorithm, right? Let us move ahead and talk about another criteria the which is stability. So if the sorting algorithm is stable or not, what does stability mean? Okay, so order of repeated elements is not changed. uh, so I think you got confused with in place, the terms in place and the term stability. So stability is something which means that order of the equal keys are going to be same even after sorting, and in place means that it is that the algorithm is not going to take up any extra space. Okay, so we say that stable and a stable algorithm is going to be something where, let me write this down, where equal keys are going to maintain the same order after sorting, right? So for now, we are going to, obviously there are more criterias with which you can actually compare sorting algorithms. There, so say for example, you have the cache performance. What is the cache performance of a particular sorting algorithm? There is the number of memory writes that you can consider for a particular sorting algorithm, number of comparisons you can consider for a sorting algorithm. But for now, let us consider only these four criterias, and based on this, we are going to look at we are going to begin with looking at bubble sort. Okay, so so let us take up an example, and with the example we are going to move ahead and look at how sorting algorithm works. Uh, you might already know about it again, but let us just review it and see how it works. Okay, so bubble sort, as you all know, is one of the simplest sorting algorithms. You might have read about it whenever you started off with sorting algorithms. So to begin understanding sorting, the first algorithm that anyone looks at is bubble sort. And what happens in bubble sort? So basically, you say that all the numbers are in form of the bubbles, and you say that the lighter bubbles are going to be moved towards the left and the heavier bubbles are going to be moved towards the right. If you are going to, let us say, sort the input array in ascending order. So we say, let us consider an example. So let us say that you have this example 7, 1, 5, 3, 9, let us suppose. And now you have to run a bubble sort algorithm on this. So what happens in bubble sort? You are going to compare the adjacent elements and then swap if they are not in the correct order. So simply this is the approach that you follow in bubble sort, which is comparing two elements and then swapping if they are not in the correct order, right? So after you compare the first two elements here, they are going to be swapped, and one comes at its correct position, and then you have 7. One here, being the lighter bubble, moves forward, which is towards the left, and the heavier bubble comes here. Now in the next comparison that you make is going to be between 7 and 5. Again, you see that 5 and 7 here are going to change their positions because 5 is a lighter bubble. Okay, now the next comparison that you make is between 7 and 3. So again, you see you have 3, 7 and 9 now. And the last comparison that you make in the first pass is going to be between 7 and 9, where you see that the lighter bubble is already at the front. Right, so this is the first pass of bubble sort, which you have, let us say, performed. Now, if you start off with the second pass, again you are going to compare with the starting from the beginning with picking up two elements. So let us consider the elements in second pass. So in second pass, again you are comparing these two elements. You see that these two elements are already the lighter bubble is already at its correct position. So next you compare the next set of elements. So you compare 5 and 3 now, but you see that the lighter bubble is behind the heavier bubble. So you bring the lighter bubble ahead, and you have this as your uh, output for after you sort or after you swap these two numbers. Then you compare these two numbers and you see that they are already at their correct position, and similarly you compare these two elements as well. Now what happens, if you can see that the array is already sorted now, but your algorithm does not know it until and unless in a particular pass you do not swap any number at all, until and unless there is no sorting, no swapping. You say that the the algorithm does not understand that the array is sorted, so it is going to move ahead and keep on comparing the elements and see if any swapping is required or not. So this is simply bubble sort. So you might be already familiar with it. If there are any questions that you have, then you can post that uh, in the group, or if you have any queries. Yes, so in place and space complexity are different terms talking about the same thing. They are not similar. We say that they are two different terms talking about the same thing. We say if there is no extra space is required, then it is known as in place. So it is a term which is defining something. Okay, so let us also now in you have already uh, uh, implemented bubble sort a lot of time, so I don't think you require looking at the pseudocode, and if it is required then you can post that in the group. I am going to write down the pseudocode as well, but I don't think it is required since it is very easy. You only run two loops starting from I, let us say, equal to 0 going on up till n minus 1, and then another nested loop inside of the I loop. You have the j loop, and simply compare two elements, adjacent elements, and swap if they are not in the correct order. Okay, so that is about bubble sort. Let us look at the time complexity. Now you know that the time, in case of time complexity, since you have two loops and you are going to start from the beginning of the array, and you can go towards the end of the array, and you can do that two times, say in the outer loop first and then in the inner loop, then you say that my time complexity is going to be order of n square. And since you can already see that you do not require any extra space, so you say that the space complexity here in this case is going to be order of 1, right? No extra space is required, so the space complexity is order of n, and this is a in place sorting algorithm because it is not requiring any extra space. And what about stability? We say yes, bubble sort is actually stable, which means that if two elements have the same key or same value, then they are going to appear in the same order as they are appearing in the original input array, right? So we say that it is stable as well. Okay, so any doubts up till here? Anyone? Shall we move ahead and talk about the next sorting algorithm? Okay, so if there are no doubts, then let us move ahead. You want to look into stability with an example. So say for example, so you will understand stability with an example wherein you have key value pairs, because in when you consider stability in terms of, let us say, only integers, then it is difficult to understand in that case. But say for example you have let us say two different names. So say for example Sumit Agarwal, and you have, let us say, Tanya Agarwal, for example. But now you see, here in this case, in Sumit Agarwal, the spelling of Agarwal is double G, while in Tanya Agarwal's name, the spelling of Agarwal is going to have only a single G. Okay, now if it is told to you that you have to sort with the last names first and then you sort with the first names. So when you sort with the last names, this Agarwal this Agarwal comes here and the other Agarwal goes down. So these two swap their positions. But when you then sort with the first names, this order is going to remain the same. But what happens in this case? The spelling of the surname that each of these two people are going to write are going to change. So this is one of the simple examples where you consider stability. Otherwise, if you want to, let us say, look at stability in terms of integers only, then you can consider your array to have two elements with the same value. And so in, let us consider the same example where you have this only, which is 71539. So you have, let us say, 7153A, let us say 9 and 3B. Let us say you have this particular array, and now once, so try to sort this particular algorithm using bubble sort, and you will see that even in the output you are going to get this value 3A first and then 3B. It is not going to be in the order of 3B first and 3A then. Okay, so this is stability. Let us move ahead and talk about another sorting algorithm. So the other sorting algorithm that we are going to look at is going to be selection sort. Again, you might have already done it a lot of times, but let us just look at how this works. So we are going to be talking about selection sort. So can anyone tell me what is the main idea behind selection sort? How is it that you approach the input array in order to sort it in the ascending order? What is the main idea behind selection sort? Yes, anyone? Search for the smallest element and swap it with the current element. Correct. So what do you do here? You simply say that I am going to find out the minimum element or the smallest element of the given input array, and I am going to put it at its correct position, right? So say let us consider the same example. So let us say you have 7, 1, 5, 3 and 9, and now you're going to swap the numbers based on the minimum element. So what do? You first find out the minimum element. So in this particular array, you find out the minimum element. What is the minimum element here? You have 1 as the minimum element here, and now you are going to swap it with the element which is at its correct position. So the correct position 1 is going to have is going to be the first position. You swap 7 and 1, 7 comes at the position of 1 and the rest of the array remains same. Okay, now what happens? You consider that this part of the array is already sorted, so you do not touch this particular part of the array. You are going to now consider only the remaining part of the array here. So again, in the remaining part of the array, since this is sorted part, in the remaining part of the array, you are going to search for the minimum element, right? So the minimum element here is going to be 3, and now you're going to change the positions of 3 and 7, which is, this position is the correct position of 3. So you pick up the minimum element and place it at the beginning. So any element which is at the beginning, it should go back to the element's position. So what do? You swap 7 and 3, and the rest of the elements are going to remain in the same order. Okay, now you consider this part of the array as sorted. So the first two elements are sorted. So after every iteration, one element is going to be at its correct position. So after the first iteration, one element is at its correct position. After the second iteration, two elements are at their correct position. Now, again with the remaining array, you are going to search for the minimum element, which in this case is 5. So 5 is already at its correct position. Now you consider the first three elements are sorted, and then again perform the same operation on the rest of the array. So let us consider another example, and we are going to see how selection sort is going to work on this. So let us say I have this array 52. Let me write this down here. So let us say you have another example. So please tell me what is going to be the array after every iteration. You should give me the output of the array. Okay, yes. So now tell me, after every iteration, what will be the output of the array, and how will you reach to the sorted array? Yes, so go ahead and post your answers in the group. Okay, so after the first iteration, when you find out the minimum element here is going to be 9. So 9 is going to be swapped with the first element of the array, that is the beginning of the array. So 9 comes at the position of 52. The rest of the elements are going to remain the same, while 52 comes at the position of 9, right? Yes. So after the next iteration, again this part of the array is considered as sorted. Now you find out the minimum among these elements. So the minimum among these elements is going to be 17, and now you consider swapping 17 with, so you have 9, 17, 33, 21 and 52, right? So up till this part your array is sorted. Again you find out the minimum element, and you say this time the minimum element is 21. So you again swap it with the first element of the subarray that you have considered. So you say 17, and then you have 21, 33 here and 52. Okay, so this part of the array is now sorted. Again you find out the minimum here is 33. 33 is already at its correct position. So the final array that you have in the sorted form is going to be this, right? So this is very simple. Again this part is again going to require, let us say if you consider the pseudocode, you're going to require an outer loop. In the outer loop you're going to start with the first element and go on up till n minus 1. Every time you're going to find out the minimum element. So let us say you have the index of the minimum element, you consider the first element as the minimum index, and then you go on find out the minimum element, and then compare every element, every first element of the subarray that you are considering with the minimum element, and swap if it is not in the correct order, right? So what is going to be the time complexity for selection sort? The time complexity was for selection sort is again going to be order of n square. Why do we consider order of n square? Because again we have two loops, and both of these loops are going to be, let us say, working starting from the first element and going on up till the last element of the array. So we consider that as order of n square. And what will be the space complexity? So the space complexity is going to be order of 1, order of 1 is not any extra space, so it means that this is a in place sorting algorithm. Now if you consider if the stability of the algorithm, we say that this is not a stable sorting algorithm. That is, the keys with different the keys with same values are going so they may or they may not change their positions in the final output that you get. Okay, so this is about selection sort. Let us move ahead and look at insertion sort as well. Okay, for so we have today, in terms of time complexity, we have discussed only those examples where the time complexity was order of n square, or let us say order of n. In the next class, that is going to be tomorrow, we are going to be also discussing about time complexity, which is going to be order of log n or n log n or like that, right? So we didn't have the complete time to look at time complexity all by itself in today's class. We are also going to continue looking at it in tomorrow's class. So we are going to begin with it like we did today, and then go on and understand about merge sort and quick sort as well. Okay, so if there is any doubt, then you can again post your queries in the group. Otherwise, let us continue and let us look at insertion sort as well. So yes, shall we move ahead, everyone? Okay, let us move ahead and look into. You did not get the staple part in selection part. We did not discuss anything about stability here. We just said that selection sort is not a sorting algorithm. If you want to go ahead, you can again consider a set of elements and use and sort them using selection sort to find out if this algorithm is stable or not. Okay. Okay, so let us understand uh, insertion sort now. So let us consider the same example that we have taken earlier, which is 52, 33, 17, 21 and 9. So we have, okay, just give me a moment. We say 52, 33, 17, 21 and 9. And now let us look at how insertion sort works. So we say, let us say that you are going to pick up two elements. So what happens in insertion sort is basically that you pick up two elements, you compare them. So once you compare them, so what do you do here? Now here is something, if you do not really know how insertion sort works, then here is something that you should pay attention to. So you say that I am going to first compare these two elements, then if I know that this particular element is less than the element that I have picked up first, then I am going to first copy the element here. So this element is first copied here, and then this element is still, let us say, in a temporary variable, and then first it is compared to the previous elements. For this particular case, you do not have any previous elements, so it keeps it in a temporary variable and then simply stores it at its correct position. So after the first iteration, you have this as the output of the array. Now it is going to pick up the next two elements. So now please focus here carefully. You say that I am going to compare these two elements. I know that 17 should come before 52. So I am going to first copy 52 here. So I first copied 52 here, 33 was here. Now 17 is currently in a temporary variable. So first what do? You keep 17 in a temporary variable. You copy 52 at its correct position. And now you compare this temporary value with the previous element itself. So this is currently, this 17 value is not copied here until it is first compared to the previous element. So first 17 is compared to 33. Now you again understand that 17 is less than 33. So 33 should come here. So you first copy 33 here and then you place 17 from the temporary variable at its correct position. So now you have 17 at its correct position. Okay, and the rest of the array remains same. Let me go over it once again. So let us do that for the next set of elements. Again, what happens? You have 17, 33 at their positions. You compare these two elements and now you keep 21 in a temporary variable. You compare temporary variable and this variable and say that my value, which is 21, is less than 52, which means that these two need to be swapped. So what I do here is I first copy 52 at its correct position, then I compare this temporary variable with the previous values, which is, let us say, this value 33. Now you know that 21 is less than 33. So what it does, it is going to first copy 33 here. Then the next thing it does is it is going to compare 17 with 21, and now it knows that 17 is smaller than 21, so it is at its correct position. So now you know that this value, this temporary value which was storing 21, should be here. Okay, so this way it is going to bring each element in every iteration at its correct position. Okay, so is that understood to everyone? Are you understanding how this is happening? Is this clear to everyone? Okay, so let us look at it once again for the last element. You compare these two elements and you say that at I am going to keep 9 in a temporary variable and first copy 52 at its correct position, because once I compared them I saw that 9 is less than 52, so I am going to place 52 here. Now the next thing that you do is you say that I am going to first compare 9 with 33. So you see 9 is less than 33, so you first copy 33 here. Okay, now again you compare 9 with 21. So you say that 9 is smaller than 21, so I am going to copy 21 here. Okay, again you compare 9 with 17. So you see 9 is less than 17, so you copy 17 at one previous position. And again you see if there is any other element before 17, but there is not, so you simply place 9 at its correct position. Right? So this is how insertion sort works. It is going to, let us say, keep your value in a temporary variable, copy the correct. So first thing that happens is it is going to keep your value in a temporary variable, then it is going to copy the correct value to its position which is the second step, and third, it is going to compare it with the previous value and see if it is at its correct position or not. Okay, so this is about insertion sort. So do you want me to write down the pseudocode, or is it simple for you guys? The time complexity here again is going to be order of n square, but if let us say your array, the array that you have is, or input array is already sorted, it is in the already sorted form, then it is going to require only order of n time. Space complexity, since you are not considering any extra space, is going to be order of 1. And when you say that space complexity is order of 1, this means that the sorting algorithm is in place, right? And if we talk about the stability, we say that this is a stable sorting algorithm. Okay, so let us also write down the pseudocode. We say that first we are, let us say, let us consider certain variables. So if we say that I am going to keep I here and I am going to keep j here, and I am going to, let us say, have a temporary variable t which is going to store 33, right? This is how it should happen, right? Temporary variable should store 33, then it should compare it with the previous element, right? So for that we start our loop for I is equal to 1 to I less than n. Why are we starting I from 1? Because we have I from here, but we have, for the other loop variable, we are starting j from this first value. So we have this as a for loop. We keep a temporary variable. In the temporary variable, we are going to store the value of a of I, right? We store the value of a of I, which is 33. And now j is going to always be at a position which is I minus 1, right? For every case, every two elements that you compare, j is going to be at the previous position. So you say that j is going to be at I minus 1's position, right? So once you have j at I minus 1's position, now what do? You are going to compare the value at index j and the value which is stored inside the temporary variable t, right? So you have a loop for that, which is going to check if j is greater than equal to 0 and a of j, the value which is stored at index j, is greater than the temporary variable value or not. That is what you do every time, right? You compare this temporary variable with the value which is at jth index, right? And why do you need a loop? Why do you need this while loop here? That is because you are going to keep on comparing with the previous values as well. So you see here, when you had 9 stored in a temporary variable and you copied 52, you had to compare 9 with the previous values, which is 33 as well, 21 as well, and 19 as well. So for that, you are going to consider a loop here. Inside the loop, if this condition is true, which is that a of j is greater than the temporary variable, then what are you going to do? You are going to swap it. So first when you store 52 at its correct position, so let us consider this iteration where you have in temporary variable you have 33, for jth index you have 52. So first when you compare 33 and 52 and find out that 33 is smaller than 52, so you keep 33 in a temporary variable and first store j at its correct position, which is at a position j plus 1. J is stored at a position of j plus 1. Every time when you move a variable, you move it towards its right. Like here as well, 17 was stored at its location, which is index plus 1. 21 is stored at its location, which is j plus 1. 33 at its location index plus 1. So what do? You say A of j plus 1 should be now storing A of j, and I will do j is equal to j minus 1. Why do you do j is equal to j minus 1? Is because now you are going to compare with the previous element. So comparing with the previous element, you will require an index which is going to track and store the previous element as well. So you do j is equal to j minus 1, and finally when you come out of this loop after comparing every time, when you want to store this temporary variable back at its correct position, when you store 9 back to its correct position, you do a of j plus 1 at this temporary variable stores a of j plus 1, right? So this is the pseudocode that you have for insertion sort. We have discussed that it is going to require order of n square time. The space complexity, since it is not going to take up any extra space, is going to be order of 1. And it is, since the space complexity is order of 1, we say that it is a in place sorting algorithm, and it is also a stable sorting algorithm, right? Now what happens, so if the array is already sorted, now this part is your homework wherein you are going to consider a already sorted array, and then using this piece of pseudocode you should run insertion sort on the already sorted array and see how many times the loop is going to run. So if you see, only n times the loop is going to run. So the best case time complexity of insertion sort is when the array is already sorted, and that time it is going to require order of n time. Okay, when array is sorted. Okay, so is this part clear to everyone? Has everyone understood insertion sort? If you have any doubts in insertion sort or bubble sort or selection sort, then you can post your queries in the group again, and we are going to take up those queries and understand. Otherwise, we had to cover these 3 sorting algorithms. We have discussed what are the different time complexities for these and the space complexity, along with other criteria which involved in place and stable sorting algorithms. So this is about it. If there are no doubts, then we are going to end this class right away, and I'm going to post a link to a test which you can attempt. So I'm going to be sending out mails for the test. Okay, so any doubts, post them in the group. Otherwise, let us end for today. And yes, so we are going to again tomorrow start off by talking about time complexities. Today we looked into all those examples where time complexity was order of n square. We are going to look into examples where time complexity is order of, let us say, log n as well, and see how that happens. And then we are also going to discuss merge sort and quick sort in tomorrow's class. So for your homework, you have to implement bubble sort, selection sort, and insertion sort yourself. Write down the code and see if it is working properly. We have already looked at the code for insertion sort. And if there are any other queries, then you can post them in the group. Otherwise, thank you for today, and let us meet in the tomorrow's class. So you want to look into stable and unstable sorting algorithms. We say that, so simply what is stability? If we talk about stability, we say that stability is something which is going to keep the order of my values. If I have 2 same values in my algorithm, it is going to occur in the same order. Okay. So that is what simply stability is, which is, say if you have 2 values which are going to have same value, then will they occur in the same order in which they were in the input? Will they occur in the same order in the sorted output as well, or if they are going to change their order. So that is what is stability about. We have discussed that only uh, for now. The three sorting algorithms that we looked at were bubble sort, insertion sort, and selection sort. So selection sort is not stable, while bubble sort and insertion sort are stable sorting algorithms. Okay, so there is this other question here, which is it possible that we take less or more space than the recursive function? If yes, then what will be the space complexity? I didn't understand your question. Take less or more space than the recursive function. What does that mean? Anshika, can you please uh, repeat your question or put it in a simpler way? Okay, so you're saying if the main function takes more or less space than the recursive function, then what will be the space complexity? So in that term, so if we let us just go back to the diagram that we looked at. So if we said that here we are considering that the main function is again going to take up k bytes, which is equivalent to the number of bytes that each of these function calls is going to take. So let us say even if this main function was taking up k minus 1 bytes or k plus 1 bytes as well, then also we are going to consider this as the same time complexity. So what in that case what you're going to have, you're going to say that I am going to have n plus 1 into k as the number of bytes that it is going to take for the function call, and let us say if I have 1 into k minus 1 or even k plus 1 or k plus 2 or whatever number here, then it does not really matter for a single function because you already have so much of space that is taken up in the recursive function only. Okay, so in that case also you are going to have the space complexity of order of n, because anyway we are going to remove the constants. Even if this expression results to something, we are going to remove all the constants and it is going to come out to be order of n only. Okay, so that was the answer to your question. If any one of you have any other questions, then you can post them. If we take up a temporary variable, we are not going to consider it as extra space. We have already talked about this. A single variable is not going to be considered as extra space. Okay, so thank you everyone. Let us meet in the next lecture and discuss. If you still have any doubts, then you can post them there.